and graph it again. So if you make a table, how many columns is our table going to have? How many columns is our table going to have? Three tables. What are the three columns going to be? Yeah, so you have t, x, and y. So when t is 1, well, actually, you know what? Yeah, when t is 0. Thank you. Yeah, when t is 0, what's x? 2. And what's y? 0. When t is 1, when t is 1, oh, you want to do it 0.5? Yeah. Okay, that's fine. If you go to a half, if t is a half, what do you get to for x? Yeah, I can estimate it's 3.5. That's right. It is 3.5 straight. And what's y going to be? 1. And then can you keep on filling in this table? Yeah, 1. And then what do you end up with for x is 1. And what's y? 0. So can you keep on filling this in? Absolutely. So this is 3, I think, right? So 3. Is that it on the left right there? Let's see here. Yep, there it is. So it zigzags around just like this. Here we go. Like this one? I think it's that one. Yeah, there you go. So if you do it out, it ends up being this right here. It's kind of cool.
Is that what meant by the scribe?
Yes.
So I don't get how.
That's fine. So at time equals 0, what point is it at? 2, 0. So right here, the particle, this is time, at time equals 0, that's where the point is. At time equals a half, what point is it at? 3 halves, comma 1. Where's 3 halves, comma 1? Right here. That's where it is at time 0.5. So the particle marches along, it goes from time 0 to time 0.5, it moves from 2, 0 to the point 3 halves 1. And then what does it do? It goes and look what it did here. At time equals 1, what's the point? 1, 0. There it is right there. So at first, it goes up and to the left. At first, it goes up and to the left, like this. And then it comes down. You're right, that was a good observation. If you jump to 1, you miss that thing. It'll go back and forth. Does that make sense? Could you plot as many more points as you wanted to? Sure. Why did we pick a half and 1? We picked it because it was kind of easy to estimate the x values and the y values here at those values, like this. Could you go finer? Could you plot more points? You could estimate more points if you wanted to.
Are we going to get the same graph?
Yeah, you should. Yes, you should. Yes. Okay, so it says for exercise 11 to 14, find the speed of the given motion of the particle. This does not ask you about the path. It asks you for the speed. It asks you for the speed. So let's transition now to a little discussion of what speed means in parametric land. Speed in parametric land, they give you this nice, they set it up as if you use 1 unit of time, where A is the horizontal rate of change and B is the vertical rate of change. How many different directions in a two-dimensional plane can you describe with horizontal and vertical change? In any direction you want to, right? So depending on the magnitude of the horizontal change and the magnitude of the vertical change, you can use the Pythagorean theorem. You know that a squared plus b squared is c squared, and you want the magnitude of that horizontal, the actual change in position. You want the magnitude of the actual change in position to get velocity. Speed is just going to be velocity without what? Without direction. Exactly, right. So in the book they go through that, and then they show you this right here, which is directly follows from the Pythagorean theorem. The velocity, the instantaneous velocity in the x direction, if it's dx dt, and the y direction is dy dt. So if you want the instantaneous velocity, what do you have to do? You take the derivative in the x direction and square it. You take the derivative in the y direction and square it, add them together and take the square root. Where does that come from? Well, v squared is dx dt squared plus dy dt squared. You're isolating v, which you want to be the velocity, instantaneous speed. It's identical to what you're doing. Correct. And we need the foundation for this because we're going to go from 2 dimensions into, and this is a direct translation. You end up with a very similar thing because the 3-dimensional Pythagorean theorem is pretty simple. Oh, excuse me. Is it a direct correlate? Does it correlate very well to 2-dimensional Pythagorean? Directly, yeah. It's really nice. So in this case right here, if we wanted to do 13, how do you find the speed of the particle? What do you do for 13? What do you have to find? Exactly. So what is dx dt in this case? 2 or negative? Negative 2 sine what? Sine 2t, yep. And then what's dy dt? Cosine t. So you know that the velocity is going to be those two things squared added together. So what is that going to be? 4 sine squared 2t plus? There it is. So what does the question ask? Find the speed for the given motion of a particle. Find any times when the particle comes to a stop. So this right here, what would you need in order to find the actual numeric value for the speed? You would need a t. Are they giving you a t in this question? No. So what is that? That is the speed. That is the formula for the speed of the particle at any time. And the second part of this question is, where does it stop? It stops when the speed is 0. The square root of that thing is 0 when the radicand is 0. So you're trying to solve this. 4 sine squared 2t plus cosine squared t is equal to what? 0. Hold on, we're doing a little timeout here, a quiz timeout here. So you had x is equal to 1/2 cosine 3t, and y is equal to 3 sine of 3t. This was almost what we talked about yesterday, almost. What's the key structural element to this parametric equation that makes it kind of nice to deal with? What's the key structural element, James Borden? They're both 3t. If they're not 3t, life gets much more entertaining. These are, so if you square both of these, what do you end up with? X squared is equal to 1/4 cosine squared 3t, and y squared is equal to 9 sine squared 3t. Is that correct?
Yes.
Oh, what happens if I just multiply by 4 now? Cosine squared 3t. And what happens if I multiply by, I don't know, 1/9? Y squared equals sine squared 3t. Now what can I do with these? If I add them together, I end up with 4x squared plus 1/9 y squared equals what? 1. Equals 1. And what is that? Oh, that's x squared over the general form, whatever you want to do. What, not equals, plus what? I just like writing it like this. Equals 1. What is that?
It's an ellipse equation.
Ellipse. The general equation for an ellipse, yeah. So that's how you would show it algebraically. Don't worry, if you wrote it out by words, it's also a way to graph it. You could make a table and sketch it. You could talk about the motion, where it starts, how fast it goes. The domain limiting, what happens after what? What does it do?
0 to 2 pi over 3.
Or any section that is 2 pi in like, well, yes, 0 to 2 pi over 3 works, right?
It was 0 plus 2 pi n.
Oh, I like that. That's cool. Yeah.
No, that's how you would went to all the time in pre-cal honors.
Well, I was in your pre-cal honors, and I would have accepted any section that is 2 pi over 3 in length, okay? Considering we hadn't talked about it, I wanted to see if you understood that it was an overlap itself.
What if we do?
I'll give you it back soon. Don't worry. You guys worried a lot, okay?
Wait, why is it 2 pi over 3?
Because, because, hold on. Let me get back to that. So, a particle moves along a curve. Find the velocity vector and the speed of the particle when t equals 1. What do we need to find for each of these components if we're going to work? Derivative. Nice. So what's x prime t going to be, Ty?
How do I know? Okay, 2 plus
2 plus
e to the
e to the t. Exactly. Lucy, what's y prime t going to be? 3. With both of these things, can we find the velocity vector? What's the velocity vector going to be? 2 plus e to the t, comma, 3. There's your velocity vector. If you wanted the speed of the particle, what do you have to do to each of those components? Square them and add them together. Moving on.
Wait, what?
Ah!
What do you mean the velocity?
Oh, who's taking physics? I was making an improper assumption. Okay. What is a vector?
You're taking it.
Are you taking?
He's taking physics.
Okay, you just got called out on record, okay? This is a velocity vector right there. It's the magnitude and the direction at any given moment. There it is. If you want to find the speed, we don't really care about direction. We're going to square it and take the square root of the sum. Are we happy with that idea?
Yeah.
Oh, so you're just saying like
So what's-
take the absolute
yeah.
value.
What's the speed? Yeah, what's the speed of this thing going to be at any given time? The square root of 2 plus e to the t squared plus 9. Yeah, okay. I'm trying to get the point across that nothing earth-shattering is happening yet. Nothing earth-shattering is happening yet. Tangent line. You have a point. If you're trying to find a tangent line and a point, what's the only other piece of information you need?
The slope.
The slope. Yes, we're going to use the derivative to find the. That's it though. That's all you need. And then what form do you leave the line in?
Y equals mx plus c.
Point
Point slope. Point slope. Point slope. Point slope. It's an abusive relationship that you have with slope intercept. Break up. Move on to the healthier relationship of slope intercept. Okay, now point slope. You're making me say slope intercept. Stop it. Okay, what's x prime t going to be, Brendan Hellweg?
X prime t is going to be 3t squared.
3t squared. And Ray, what's y prime t going to be?
2.
Equals 2. So what's x prime t? Well, what's x prime at? What was it at? Ooh, we have to be careful, don't we? We have to be,
Yeah.
oh, we don't have time, but can we find time?
Yeah.
Yeah, we know that we're looking for it when the time when x is 1. So 1 is equal to t cubed, so t is going to be, and that, oh, wait, oh, does it match over here? 2 is equal to 2t, so t equals 1. Should they match? They better match, or we have a problem, because if they don't match, it doesn't pass through that point. It's a problem. You know, for example, if I chose the point like 68 comma pi, right? That's a point technically, right? But if you try to solve for the time, what happens? You end up with an inconsistency. It doesn't pass through that point. So if we end up with 1 here and 7 here, what does that mean? It doesn't pass through that point, 1, 2. Oh, we know what the time is now. The time. What time is it when the particle passes through 1, 2? 1. So what's x prime of 1? 3. What's y prime of 1? 2. Exactly. So what's the slope going to be right there?
UID.
9 plus 4.
Not asking you for the speed. Tangent line, what do you need? I pivoted pretty quickly here. Tangent line, what do you need? Point and slope. What do we have?
We have a point.
We have x prime and we have y prime. So what's the slope there?
2 over.
Come on, take a stand, everybody.
No, yes.
2 over 3. The slope is going to be 2 over 3. Be careful. This is not the speed of the particle. This is the slope of the tangent line. The slope of the tangent line. You were mentioning this before. I heard you mentioning this when you guys were working on the homework. If you want dy dx, and y is written in terms of t, and x is written in terms of t, what do you take? dy dt over dx dt. That's a result of the chain rule. That's a result of the chain rule right there. Why is that a result of the chain rule? Because, what does this look like right here? If I move this right over there, if you take dy dt, where y is equal to f of x, but x is equal to some function in terms of t, what do you have to use in order to compute that derivative? You have to use the chain rule. Yeah, implicit differential, the chain rule, right? It kicks out and then you divide. But so the idea is, if we want to find the slope at a given point, we need the rate of change of y and the rate of change of x, and then we write them as a ratio. That's it. The notation looks heavy. In practicality, the application is rather straightforward. Say, do we have a slope? Yeah, we do. We have a slope, and what's the point?
1.
I think it was 1, 2.
1, 2.
So once you have that, you are done with the problem as long as you write y minus 2 is equal to x minus 1. Stop. Do not put that into slope-intercept form. You're going to do that 100 times, and like 6 times you're going to get it wrong. And then we'll be very sad because you won't get the answer point and you've wasted a minute. Have something like maybe x is going to be cosine something, and y is going to be cosine something, right? We have a thought. What do we need to add in front of the x thing?
You need to add.
Let's rewind for a second because I'm getting some shaking heads in the back, okay? Oh! Did we write something like that before, earlier in this class?
Yeah, we did.
We did.
Yeah.
Before in this class, on the quiz that you had today, I had you build an ellipse. Ellipse. Exactly. So, I have another question. Could we just as easily flip these if we wanted to? Could y be cosine and x be sine?
Why are they?
We can
Oh,
start-
all right. Hold on. Let me clean this up. I'm sorry.
We can start wherever we want.
Is if you picked, for example, x is equal to a half cosine theta and y is equal to sine theta, what happens if you square these, Jesse? X squared equals cosine squared theta and y squared is equal to sine squared theta. Now, if we were to multiply the one on the left by 4, we don't really like that 1/4, right? If we multiply this by 4, what do we get? Cosine squared theta, and we still have over here, we're not multiplying sine squared theta. Now when we add these, what is cosine squared plus sine squared? 1. And what are we left with on the left? 4x squared plus y squared. So yes, it was presupposed with my very accurate guess of having a 1/2 right here, correct? So if that's a 4, what do we have to put right there? 1 over the square root of 4. Because we know we're going to be squaring both sides and adding them together to apply that trig identity. Sine squared plus cosine squared is 1. Parametrization means writing the equation in parametric form. Writing the equation in parametric form.